Isn't this a great joke? All right, so today we are going to be discussing infrared, so infrared spectroscopy. Right, it's another type of spectroscopy that organic chemists use to find out a little bit of information about their molecules. And so what we use IR spectroscopy for is to find out what functional groups are present. So remember, we use at C13 NMR, and next semester we'll talk about proton NMR. We use that to help us figure out what the carbon-hydrogen framework of an unknown molecule is. And we use IR spectroscopy to determine functional groups. And so like C13, there are certain areas where certain functional groups show up, and you are going to have to be familiar with what those areas are. So we'll start with this, but I actually like it in this order, so I'm going to turn it upside down on you. The electromagnetic spectrum. So I like low energy to start over here, and then higher energy frequencies to come over here. So I like my energy to go in this direction. And so again, our lowest energy waves are radio waves, and you will remember, well, you can see that. Let me look a little closer. You will remember that we use radio waves in NMR spectroscopy, right? That is a low energy radiation. All we're trying to do in a molecule is to flip the nucleus, right? So flip the spin of the nucleus, right? That's what we're trying to do in NMR spectroscopy, and so that does not take a whole lot of energy, and so we use radio waves to do that. The next highest waves are our microwaves. Again, that has to do with rotation of bonds, and that's what cooks our food, particularly rotation of the polar HOH bond, or sorry, the HO bond in water. And then next we have infrared, which we'll talk about. Then you have the visible light spectrum in here. And finally, above visible light is when you can actually when you can actually break bonds, right? So it's not till you get to the high energy UV rays where you can actually break covalent bonds. And then you have X-rays, and then last you have gamma rays. Okay? So that's your electromagnetic spectrum. Let's talk a little bit about what's happening in here. So if this energy is enough to get our nuclei to spin flip, what is it that the frequencies, and you can see there's a whole range of frequencies here, right? There's lots of different frequencies that fall into the IR range, right? If a molecule absorbs IR light, what is it causing the molecule to do, right? So it's not causing the nuclei to flip, that's down here, and it's not breaking covalent bonds, that's up here. Right, so what happens with infrared? It's not rotation of bonds, that's what microwaves do. What infrared light does, or infrared radiation, is it actually gets your bonds to bend and stretch, right? So if bonds are stretching like this, or asymmetrically stretching like this, or bending, or wagging in and out of the plane, that was a little bit harder to do. Right, all of that, all of those motions are because the molecule has absorbed IR light, right? And so you are going to see that certain functional groups will absorb very specific frequencies of infrared light, and therefore that absorbance will be recorded on the instrument, the IR spectrometer, and then you will be able to interpret the spectrum that comes out. So it's very quick, it's very easy. It gives you a little bit of information about your molecule because it gives you information about what functional groups are present. And again, not all functional groups are IR active. We'll see why, or we'll see which ones, but many of them are, and that actually is often very helpful when you're trying to figure out what your molecule is. So, you have this picture in your manual, right? So hopefully you have your manual and you can find this picture. And so when we say that a molecule will absorb IR light, again, remember each frequency of IR light is a very specific amount of energy. And so a bond, right, it's not like heating up a molecule where, or heating up a solution where you're taking all of that heat and increasing the temperature. Here, if you have a specific bond in your molecule and you want that bond to stretch a certain way, right, or you want it to stretch, right, that's one specific frequency, that's one quanta of energy that needs to be absorbed by that molecule to get that one bond to stretch. And if you want that bond to bend, right, well, that's a different frequency. Right? So molecules will actually absorb a fair amount of infrared light because they're all bending and stretching, and you have the pleasure of interpreting the spectrum that comes out of that absorption. So when you look at an IR spectrum, usually starts, for organic, we tend to start about 4,000 down here, and we usually go to about 800 on this side. And the units associated with IR, so remember the units for NMR are either delta units or ppm. The units for IR are inverse centimeters, right? Because we measure this in what we call wave numbers. And wave numbers are essentially 1 over the wavelength. And if your wavelength is measured in centimeters, then your wave number is in centimeters to the -1, or as we say, inverse centimeters. The reason we don't use wavelengths is because wavelengths tend to have values, some number times 10 to the 4, some number times 10 to the 6, right? So to simplify it, if you take the inverse of that number, you're going to get a number like 2100, right? It's much easier to work in wave numbers than it is to work in actual wavelengths, but they're easily interconvertible. So we do have units of inverse centimeters associated with our peaks in the spectrum. Unlike NMR, where we would call this the downfield end of the spectrum and this the upfield end of the spectrum, we don't use those words in IR, right? So in NMR, we use upfield and downfield to talk about positions on the spectrum. In IR, we do not use those words. So don't tell me that these peaks are downfield from these peaks, right? Because that's not a lingo that is used for IR spectroscopy. If you want to talk about these peaks, we tend to just talk about what is their actual wave number relative to this. Okay, so that's, just keep that in mind, because I often hear people try to describe this as downfield because you're used to it from NMR. It's just not interchangeable between the two types of spectroscopy. You will also see on the bottom that I've labeled this region the diagnostic region. It usually goes to about 1500. We'll call it at 1600. So from 1600 to 4000, that is termed the diagnostic region. And then from 16 to 800 or down here, this is called the fingerprint region. Okay, so this is called the diagnostic region. That is the region that we are going to focus on. That is where the peaks associated with many of the functional groups show up, and they're pretty distinctive, right? They're pretty diagnostic. So we're going to interpret this part of the spectrum. We are not going to look for peaks in the fingerprint region. But the reason this is called the fingerprint region is that every IR, or the IR of every molecule is different. So if you have hexane and you have heptane, yes, those two molecules differ by a CH2 group, and their spectrum or spectra will look virtually the same, but if you really mapped out things in this fingerprint region, you would find where the differences are. And so every single molecule has a different IR spectrum, and that difference is generally found here in the fingerprint region. We are not going to get so deep into IR spectroscopy that we need to worry about this region, but you should know that lots of things show up here, and particularly to organic chemists, carbon-carbon double bonds are down in this area, carbon-carbon single bonds are down in this area, carbon-oxygen single bonds are down, lots of single bonds are down in this area, and so it is not an area to completely ignore, but just to recognize that there's always going to be a whole lot of peaks down here. Okay, so I think I don't have these in quite the right order in your manual, but now you want to go to this chart that says characteristic frequencies. And I'll go through and mark up the ones that you're going to have to know and where you're going to see specific examples of these in the later pages. But you will certainly, let me say this, when I say know, I mean be familiar with, right? I do not in any way expect you to memorize these numbers. Because again, an alcohol peak, might be slightly here, might be slightly here, more likely slightly here, right? And you're going to say, oh, it's below 3,400, so it can't possibly be an alcohol, and that's absolutely not true. So just notice that these regions differ very much from these regions, right? So we'll do specific examples of them. And I've got to find a pencil that works. There we go. So you will have to know OH, you will have to know NH, you will have to know this is the CH bond here of a triple bond. You will have to know that. This is that part of a carboxylic acid. You will have to know that. These two I want to very specifically talk about. And so you will notice that this says CH, and these are CH stretches out here. This is going to be a hydrogen that's bound to a carbon that's part of a double bond. And you can see for aromatic, if you think about an aromatic or an arene ring, that carbon hydrogen, that hydrogen is bound, no matter where it's bound on that molecule, it's bound to a carbon that is a double bond, is an sp2 carbon. And so these types of stretches, right, these are the carbon hydrogen stretches, we actually call this, for simplicity's sake, CH unsaturated. Right? That simply means that if you see peaks in here, it means that you have some kind of unsaturation. You can't tell whether it's a double bond or an aromatic, but you can tell that you have some kind of unsaturation in your molecule. And then 3,000 to 2,800, right, then you have just CH saturated. Right, and that's regular CH3, CH2, CH, and if you think about organic molecules, there's generally always some kind of alkane-like portion to your molecule, so you virtually always see peaks in the 3,000 to 2,800 region. It's not diagnostic, but it is telling it is helpful. And so if you look at these regions, 3,100 to 3,000, 3,000 to 2,800, it turns out that this 3,000 value really is very distinctive. So that is one number that you do want to recognize. Because if your peaks are above 3,000, 3,052, that starts to tell you that you have unsaturation. But if all of your carbon-hydrogen peaks, absorbances, are below 3,000, then you can say you don't have these things. Right? So that 3,000 mark really is pretty distinctive. So remember that one. Then in an aldehyde, notice that this is an and not a range. Right? These other ones are ranges. This is an and, meaning that if you have an aldehyde, this carbon-hydrogen bond will show up as a peak at 2820 and 2720. And again, it might be 27, 22, 28, 21, right? But it's two separate peaks. It's not a region. It is two separate peaks. Again, we'll have an example of that. And then here you can see that your carbon-carbon triple bond and your carbon-nitrogen triple bond are basically the same region. And so your triple bonds, right, can you tell whether you have a carbon-nitrogen or a carbon-carbon triple bond? Not generally, not from the start. You would know you would have one of those two, and then you use your C13 NMR to tell you some more information about what it might be. But notice that region, I mean, I know it's different here, but they basically are the only things that show up in this range. Next, carbonyls. So you know that anhydrides, acid chlorides, esters, aldehydes, ketones, acid, and amides, they all contain a carbonyl. On a test, I only need you to be familiar with this region. Right? I'm not going to ask that you remember all of the different regions of carbonyls. I just want you to be able to look at a spectrum and say, is there a carbonyl in there? And then what other information might I have that could tell me what type of carbonyl it is? On a homework, though, and on a lab assignment, when you have access to this piece of paper, I do expect you to use this piece of paper to determine what exact type of carbonyl your molecule is. Okay, so recognize that difference on a homework. When you can look at these values and compare them to your problem, then I do expect you to use this sheet. But on a test, I only need you to recognize the general, broad, 1650 to 1850 range. Okay. And then we're not going to do, from benzene ring down, we're not going to do any of these. Right? So nothing in here. So you can see that different functional groups do show up down here in the fingerprint region. We're just not going to go searching for them. This is just another way to look at the data. Some people would rather look at it graphically like this instead of a list. So that's why that is there. And so now let's look at, and we're going to look at these sort of individually. Right? We're going to go through a couple of spectra so that you can see what the spectra look like. So when you look at this molecule, you will notice that it is an alkene. And because it's an alkene, right, in this case it has 3 hydrogens that are bound to carbons that are unsaturated, bound to carbons that are double bond. And so you should expect that you would have peaks slightly above 3,000 because these hydrogens are going to absorb there. And that's what you see here, right? And then you see a whole lot of peaks in this region, right? A lot of these frequencies are absorbed because you have a lot of carbon-hydrogen bonds in there that are bending and stretching. So lots of different frequencies are absorbed in here. So you're going to notice when you look at a spectrum that you are going to almost always see peaks in that region, right? Because all organic molecules, well, almost all organic molecules have that, right? So that's sort of a good place to start looking and say, all right, I'm going to divide my spectrum up. I'm going to call this area here fingerprint, so I don't care. Then I have this region in here. You're going to see this region in here. The only thing that shows up here are carbon-carbon triple bonds and carbon-nitrogen triple bonds. And then I have my CH saturated. And in this case, at 3078, I'm actually seeing CH unsaturated. So these are CH saturated, and that is CH unsaturated. And these absorbances in here, again, are because of the 3 hydrogens bound to those carbons. They are CH stretches, though. All right, let's look at the one next to it. When you look at this spectrum, again, fingerprint, don't care. When you look in here, what do you see? 29 something, 28 something, right? These are CH saturated. If this is my molecule, I have lots of CH saturation in there, right? So of course I'm going to have stretches in here. But when I look at this spectrum, this piece over here is a dead giveaway to me. And so if I see, right, these are my CHs. If I see in this region a somewhat rounded peak, that is an OH, right? That tells me I have an OH in my molecule. You're going to see, if we go right below it, right, there are three things that absorb out here, and the only way to really tell them apart is by shape. And so if you determine that your peak is rounded, right, then you know your molecule has an OH. But if you look at the spectrum right below it, again, fingerprint, don't care, no triple bonds, CH here. And then I look at this, right? When I look at this one and the one above it, they look different to me. In particular, this one looks different because there are two little nubs here, right? I call this a cow udder, because that's what it quickly looks like to me, right? This is indicative of an amine, and if you have two little peaks here, then you have two hydrogens on your nitrogen, right? So if I have two hydrogens on my nitrogen, I'll see two little peaks here. How does this amine, what if the amine only has one hydrogen? If it only has one hydrogen, again, this is the nitrogen-hydrogen stretch. So if it only has one hydrogen, how would I know if it's an amine or if it's an alcohol? That is simply a shape. Right? I'll go back up here, and if I had one hydrogen, just one hydrogen and then some R group, then it would probably look, you know, a little bit more like that. Right? It's not nearly as round and as usually deep as alcohols are. Right? So you're using shape to tell the difference between the amine with one hydrogen. If it has two hydrogens, you'll see two little nibs. That's a dead giveaway that you have what we would call a primary amine, or a nitrogen with two hydrogens on it. If you have an amine with no hydrogens, then you will not see a stretch out here, right? Because this is the NH area of the spectrum, and if you don't have any NH bonds, then you won't be absorbing anything. So you could have an amine in your molecule, but it just wouldn't have any absorbance here because you don't have any if you had this. Right, R, then you would just have a flat line here. So far, two things that show up higher, in higher wave numbers than our CHs, are our NH stretches and our OH stretches, and the one other thing that shows up in this area is right here. Okay? And so if you look at this molecule, it does not have a heteroatom. There's no OH, there's no NH. It actually has a carbon-carbon triple bond. And here's where you have to be careful. The carbon-carbon triple bond stretch that the frequencies that absorb for the carbon-carbon triple bond are right in here. Right? So remember, this region of your spectrum, triple bonds. And so you see peaks. The triple bond peak is always a small peak. It's never a deep peak. And so you have that identified as a triple bond. CH stretches here, fingerprint here, but the dead giveaway is right here, right? And if you look at this shape of this peak versus the shape of the NH peak versus the shape of the OH peak, you can see that they are in fact very different from each other. right? OH would be rounded here and probably not as deep. NH or NH2 would be looking more like this. And so this very sharp peak, that is a very sharp distinctive peak. If you see that, and you should see this, this is due to the carbon-hydrogen end of your triple bond. So if you have a triple bond that has one of the ends of that triple bond is a hydrogen, it's this carbon-hydrogen peak stretch that you will see right here. If this is not a hydrogen, if this is an R group, you might still see the triple bond because you do have a triple bond, but you won't see this peak because you don't have a hydrogen there. This is strictly a carbon-hydrogen stretch. And so this sheet, right, when you look at these examples highlight for you what you saw here. Right, I'll bring this down. Right now you know that OH and NH and this hydrogen are all in sort of the same area of the spectrum, and then I get my CH stretches, either saturated or unsaturated, and then I have my triple bonds, right? And then the only last thing we have to talk about are our carbonyls. So the next sheet gives you some samples of carbonyls. Not that sheet, that looks like an alcohol. How about that sheet? That's better. All right, so I'm going to put all 4 of these up here because that's the page you're looking at. When you look at these spectra, what they all have in common, fingerprint aside, CH stretches aside, right? They all have the CH stretches. What peak-ish, not overtone, what peak seems to be very distinctive, very deep, and common on all of them? And hopefully you've looked at your spectra now and you can see that this peak around 1700 and in the 17s and in the 17s and in the 17s, right? This peak in all of them is the carbonyl group. The carbonyl stretch is very distinctive in a spectrum. You need to be able to look at a spectrum and instantly determine whether that molecule has a carbonyl or not. Because you're going to see, again, fingerprints here. The only thing that absorbs 1650 to 1850 is your carbonyl. And so, and they're distinctive stretches. They're deep, and you can spot them. And so you should be able to look at these spectra and automatically say there's a carbonyl in each one of them. And also each one of them happens to have CH stretches. And don't worry about, but ignore overtone. That's why they're telling you it's an overtone. There's no OH, there's no NH, right? This is an NH, this is an overtone. But the top 2 have other peaks that maybe you can recognize. So let's start with this one. So you see a carbonyl, and you see your CH stretches, but outside that 3,000 to 2,800, you actually see a 2721. And if you see a 2720 something, if you see that peak, you have to immediately look to see if there's a partner, right? Because remember, an aldehyde has 2 peaks. 2720, 2820, right? They're not huge, right? So they're going to be small like this, but you have to see if there's a pair. You might see a 28 something, but you don't see the 27, then it's not an aldehyde. But if you see the 27, look for the 28. Sometimes it's marked for you, sometimes it's not marked for you. You might just see it there, and you'll say, oh, if this is 2772, then this has to be less than that, and that's probably the pair. Okay, so for an aldehyde, you have to have 3 peaks. You have to have the carbonyl, which is the CO stretch, and then you have to have 2720 and 2820 little peaks over here. And if you have all 3 of those, then you know you have an aldehyde in your molecule, which you do here. And again, this just reinforces what are the structures of our functional groups. Okay, so then we have CH stretches and fingerprint, and that's it. So remember, you need that peak, you need that little peak there, and you need that peak to be a carbonyl. I'm sorry, to be an aldehyde. Now, when you look at this spectrum, you should immediately say that this spectrum doesn't look like any of the others we've seen. You have fingerprint, you have a very strong carbonyl, but then you have this whopping wide peak here, right? Even an alcohol, which is roundish and deep over here, is deep, comes back up to the baseline, and then you have CH stretches. Look at how wide this is. If you have a carboxylic acid in your molecule, you will have 2 peaks. You will have the carbonyl stretch, but then you will also have this very wide stretch here, right? This is indicative of a carboxylic acid, right? That stretch is about 3,500 to 2,500, right? It's wide, it's the widest stretch we have, and it's really easy to identify. So you need this stretch, and you need this, and you have a carboxylic acid. And what you see peeking out under here, right, are some of the carbon hydrogens. You know this is 30-30, and this is 28-31. You know this is the region for carbon-hydrogen bonds. And they're absorbing as well. They're just coming out underneath the big carboxylic acid peak, which usually swamps everything. And so, you know, when you see 30-30, you should say, oh, I have some peaks that are carbon-hydrogen unsaturated. I look at my molecule, I have 1, 2, 3, 4, 5 of those hydrogens. And then I have other hydrogens that are carbon-hydrogen saturated. So that's what's happening here. This, when you see a carboxylic acid, it's sort of like seeing an alcohol. Those are easily identifiable peaks. But remember, you need this stretch and this stretch, because this stretch is the CO part of it. This stretch is the carboxylic acid. Okay. So now we're going to look at the bottom 2, and let's look at them together. When you look at these spectra, you see fingerprint, you see a carbonyl, you see no triple bonds, no triple bonds, you see CH stretches and CH stretches, and then you see no OH or NH or hydrogen on a triple bonded carbon. And so these spectra to me look, I mean, they're not identical, but they're incredibly similar. And so what I'm trying to say to you is that on a test, I would not ask you to differentiate these 2 molecules. This one, if you look at the functional group, this one is a ketone, this one is an ester, right? They both contain a carbonyl, and then everything else is distinguishing them down in the fingerprint region. So on a test, I would not give you both an ester and a ketone as choices and make you choose. But on a homework or a lab assignment, I can ask you to tell me which is the ketone and which is the ester, because you have this sheet, and you can go back to this sheet, and you can look very specifically at the regions that you need and say which one of these functional groups it is. So in the first case, 1717, right? That looks to me like it falls here in the ketone region. It also falls in the aldehyde region, but I don't have the aldehyde hydrogen stretches, so I know it's not an aldehyde. So I could label this one a ketone. And if you look at the stretch for the carbonyl here, it's 1742. And if I go back up into this sheet and look for 1742, I end up with an ester. So for a homework, I do expect you to use this sheet and specifically tell me what molecule, of the choices that you're given, what molecule it is. On a test, I would not do that to you. Okay. So, usually at this point I use the board, but since I don't have a board, I'll use a piece of paper here. What you should be familiar with. I would say that if you have an IR spectrum, I'll put a line here at 2500. I'll put a line here at 2000. 2000. I'll put a line here. And I'll make this 1500, and these are all inverse centimeters. And these are just approximate lines. But this, 1500 and below, is your fingerprint region. And then in here, say 2000 to 1500, right? That's where we find our carbonyl groups. We also find our carbon-nitrogen double bonds and our carbon-carbon double bonds, but we're not going to worry about those. And then 2000 to 2500, right? The range is technically smaller than that, but I'm just keeping the numbers round. That's our triple bonds. Remember, we cannot have a carbon-oxygen triple bond because that's too many bonds to oxygen. And then in this region, you have your OH, your alcohols were there, you have your NH, your amines were there, and you have your CH, right? And so you're going to remember very specifically the 3000 mark, and if my stretches are below that, I have CH saturated. 100 to 3000, I have CH unsaturated, and my OH and my NH and my hydrogen bound to a terminal triple bond, the end of a triple bond, are going to be even further at a higher wave number than that, right? But this is approximately what you have to recognize for an IR spectrum. So here's a typical question. Get it all on the slide. I'm going to, on a test, and this is, again, this is a topic that comes back into the classroom, so we use spectroscopy in lab, we also use it in the classroom, we use it a lot in word problems. But here's a spectrum, and then below that are 6 choices, and this is just a multiple choice question. This IR spectrum represents which of these molecules. And so I'm going to ask you to stop the video, and the way that you approach this problem, of course there are 2 ways, but I would look at the spectrum and say, what do I see and what don't I see? And then I would go through my choices and try to figure out what I should see and what I shouldn't see in each one of those molecules. And so let's just be clear. This is a carboxylic acid. pH stands for phenyl, which is this aromatic ring, drawn out for you. So you're an alcohol, here's an amine, here's an amide, it's a triple bond, terminal triple bond, and then an alcohol. So go ahead and stop the video now, go through all those choices, figure out what you think the answer is. So now that you've come back, when I look at this spectrum, I instantly see an alcohol, right? This is a classic alcohol stretch. So I know I have an alcohol in my molecule. CH saturated, that doesn't help me very much. No triple bonds, no carbonyl, right? So no carbonyl and an alcohol, I ought to be able to figure out what my spectrum should look like, or which one of these choices it is. So I'm going to look at these choices. Carboxylic acid. Carboxylic acid would need to have a carbonyl, and it has that really wide 35 to 2500 stretch, right? So not A. B is an alcohol, could be a possibility. C is an amine, right? And it's amine with one H. And so, yeah, it has a stretch out in that same area as an alcohol, but this was a nice, round, deep, definitive alcohol stretch. So I'm going to cross out C. D, also an alcohol, so I'm going to keep that. And then E, right? E would have a carbon-carbon triple bond in the 2100 region, which I don't see. Also would have that really sharp carbon-hydrogen stretch, 3300 or so, out where the alcohol is, but by shape that is clearly an alcohol and not a sharp, significant absorbance there. So we're going to cross out E. And then F, again, I have an NH here, so it would look like this, and since I already crossed out that, I can go ahead and cross out this. Also, this amide has a carbonyl, and I don't see a carbonyl, so I'm going to go ahead and cross out F. So really I'm choosing between B and D. And so here's where it gets technical. What's the difference really in an IR spectrum between this structure and this structure? And the answer is that this structure, everything is saturated here, right? They're all carbon-hydrogen saturated bonds. There's no double bonds, there's no aromatic ring. So all of these stretches should be between 3000 and 2800. If I have this molecule, these stretches, right, these hydrogens would be between 3000 and 2800. But these hydrogens would be 3000 to 3100. So I have to look closely at that region where the CH stretches are to see the 3000 dividing line, and do I have peaks above it or not? And so when I go back to this peak, or this spectrum, right, my 3000 line, that's going to be somewhere in there, but I can look at that and tell you that this is 2927, this is 2860, so these are all CH saturated. I don't have anything from 3000 to 3100, so that means that my choice has to be D, and it cannot be B. Okay, so these other ones you could cross out pretty easily. These two, you had to really take a close look at that region and say, are there peaks above 3000, well, 3100 to 3000 or not? Okay, that's what you were looking for there. All right, so the last thing, your assignment. So your assignment for the IR portion of the laboratory is due the week you come in to do your recrystallization. And so you have to make sure that you've watched this video and have done the assignment before that date gets here. And this little sticky note is just telling you that if you're an aldehyde, this IR assignment is due October 26, 27, and if you're a ketone, it's due November 2nd and 3rd. Okay. And all that's due here is that I've given you 7 spectra. So you will see right after this page that there are 7 different spectra there. And I'm asking you to identify which spectrum belongs to which of your choices. So you have choices you have 10 choices and only 7 spectra. So you're going to have some choices that don't show up here. And please, please, please remember that each spectrum Now each molecule has its own spectrum, so don't give me two of the same letter up here unless you're totally confused. But each one of these should be a different letter. And so what I need from you when I say that this assignment is due is you can either rip this page out of your lab notebook, or you can just retype spectrum 1 and tell me what letter you think it is, and spectrum 2 and tell me what letter you think it is. So I only need this. I don't want to see your 7 spectra. I don't want to see how you've marked them up. I'm going to trust that you can do that. If we don't get the right answers, we can go back and look at those, but you do not need to send me all of the 7 spectra. You just need to send me your answers. So that's what's going to be due. Right? And again, same thing. Look at your look at the first spectrum that shows up, see what functional groups do you think you see, what don't you see, and then start looking at all of these choices, right? Recognize what the functional groups are in each one of these choices, right? Functional groups will come back to haunt you, and certainly in IR spectroscopy, okay? So that is what is due. You have your due dates. Those are the same due dates that are in your syllabus. I just pulled them out a little bit for you. And that is the end of our IR spectroscopy chat. Please let me know if you have any questions, right? Again, this is going to come back on your tests, and well, you don't have quizzes this semester, but back on your tests, and so you really have to have a good understanding of this. So if something is confusing, please, 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 let's get that cleaned up before it shows up anyway. All right, enjoy!